My wonderful Masters vs. students, you are welcome to another class of chemistry. I remain Mr. Odemenam, your chemistry teacher. Today we will be looking at SS3 students. We've already started this topic, which is sodium and its compound. Today we will be looking at compounds of sodium. There are so many compounds of sodium, but there are few number of compounds of sodium that are written on the board. You know of so many other compounds of sodium. We have, as an SS3 student, you are supposed to know the names of these compounds that I wrote the formulas. The first one there is sodium hydroxide. The second one here is sodium trioxocarbonate 4. The third one is sodium chloride. The fourth one is sodium tetraoxosulfate 6. The fourth one is sodium hydrogen trioxocarbonate 4. We will look at sodium hydroxide first. I'll be using equation. You are in SS3. I'll be using equation to write most of these things because you are supposed to know their names. Sodium hydroxide, another name of sodium hydroxide is caustic soda. And you know that sodium hydroxide is a heavy chemical. Being a heavy chemical, you know what it implies. It implies that it is produced in large quantity and also used extensively in large quantity. It's a heavy chemical, and I've explained to you what a heavy chemical is. We'll look at preparation and production of sodium hydroxide. Preparation and production of sodium hydroxide. What we are looking at this time is sodium hydroxide. We'll look at preparation and production of sodium hydroxide. The preparation is mainly the lab preparation or preparation in small scale, while the production is production in large scale. There are two methods of production of sodium hydroxide. The first one is Gossage Process. And the second one is electrolysis. The first one is Gossage Process, and the second one is electrolysis. Under electrolysis, there are two types of cell. The first one is Kerner-Solver process, and the second one is diaphragm cell. But let us look at Gossage Process first. Gossage process is actually double decomposition. If you react sodium trioxocarbonate, if you heat sodium trioxocarbonate 4 with calcium hydroxide, there will be double decomposition. you will produce your sodium hydroxide and calcium trioxocarbonate 4. Therefore, what we are discussing now is Gossage process. Gossage process, you can write, is a process of producing sodium hydroxide by heating sodium trioxocarbonate 4 with calcium hydroxide. You have this equation: sodium trioxocarbonate 4 aqueous plus calcium hydroxide to give you, this is aqueous to give you calcium trioxocarbonate 4 precipitate plus sodium hydroxide. Therefore, if you look at this equation, you discover that is double decomposition. Double decomposition because the first compound here, sodium trioxocarbonate 4, is split into sodium ion and trioxocarbonate 4 ion. And this calcium hydroxide is split into calcium ion and hydroxide ion. This sodium will exchange itself with calcium. That is double decomposition. You can see that we have produced sodium hydroxide. If you look at this right side of the equation, you discover that the calcium trioxocarbonate 4 is a precipitate and that the sodium hydroxide is aqueous. Since calcium trioxocarbonate 4 is a precipitate, it means that you can filter out calcium trioxocarbonate 4 out. After filtering it out, the filtrate contains sodium hydroxide. That filtrate that contains sodium hydroxide, you can concentrate it by evaporating excess of the water that is in sodium hydroxide, and then after concentration, you will now do crystallization to obtain your sodium hydroxide. That is about Gossage process. Let me go to Gossage process is a process of reacting sodium trioxocarbonate 4 with calcium hydroxide to produce sodium hydroxide. That is the Gossage process. Let's now look at the industrial manufacture or production of sodium hydroxide. Like I've already told you, I said that there are two types of electrolytics used in production of sodium hydroxide. You have the You have the kernel solvent cell. And the diaphragm cell. You have the kernel solvent cell and the diaphragm cell. But let's look at how you can equally produce sodium hydroxide even in the lab without using these two cells. If you have your beaker, and in that your beaker you have you dissolve sodium chloride in water, then you have two electrodes. In the two electrodes, you have your graphite anode. The anode is positively charged, and you have your iron or steel cathode. Cathode is negatively charged. Then you have you now connect it to a battery. Connect this one to a battery also. I've already taught you that at the site of the anode is where oxidation occurs, and oxidation is loss of electron. At the negative electrode is where reduction occurs, and the negative electron is where reduction occurs. Therefore, if you have your sodium chloride solution, aqueous, you discover that the ions you have in that aqueous sodium chloride will be sodium ion, chloride ion, hydrogen ion, and hydroxide ion. The sodium ion and the chloride ion is from sodium chloride, while the hydrogen ion and the hydroxide ion is from water. Therefore, you discover that sodium and hydrogen ion will migrate to the cathode. Unlike charges attract, sodium and hydrogen ion will migrate to the cathode, while chloride ion and hydroxide will migrate to the anode. We have done electrolysis. When we did electrolysis, we discovered that if sodium and hydrogen ion migrates to the cathode, because hydrogen is very low in the electrochemical series, hydrogen will be deposited or liberated on the cathode. Then when you come to the anode, you have chloride ion and hydroxide ion. You discover here that because this is a concentrated solution, and also their placement in the electrochemical series, the chloride ion will migrate to the be liberated on the cathode. But let us look at reaction that occurs on the anode. At the anode. At the anode, what goes there is chloride ion. 2 moles of chloride ion will go to the cathode and will go to the anode, The chloride ion will go to the anode because it's at the anode that oxidation occurs. Then when it goes to the anode, it will lose 2 electrons there. You have Cl to form chlorine molecule or chlorine gas plus 2 electrons, leaving hydroxide ion in the beaker, leaving behind hydroxide ion. Then at the cathode, I've told you that at the cathode, you already know it, that at the cathode, that is where reduction takes place. And reduction is addition of electron. Therefore, the electron produced at the anode is now gained by hydrogen ion. 2 moles of hydrogen ion plus 2 electron will now give you hydrogen gas. You see that the product of electrolysis at the anode will produce chlorine gas, and the product of electrolysis at the cathode will produce the hydrogen gas. If you look at this thing, you see that these ones that I'm going to underline now, the sodium ion and the hydroxide ion, are left behind in the beaker. And when you add sodium ion plus hydroxide ion, you will now get your sodium hydroxide. Okay, can you list the products that we're able to realize from electrolysis of sodium chloride? Yes, you said what? You said calcium. No, calcium is not there. What you produce in the electrolysis of sodium chloride are 3 products. One of it is sodium ion. One of it is hydrogen gas. The second one is chlorine gas, and the third one is sodium hydroxide. The hydrogen gas is formed at the cathode, and the chlorine gas is formed at the anode, and the sodium hydroxide is left behind in the beaker. You can see that this is a simple cell. What we use in producing this is a simple cell. But in industrial process, you cannot use this simple cell, because why you will not use this simple cell is that if electrolysis is prolonged, you discover that some of the product of electrolysis will react with other things there to give you. You discover that chlorine which you have produced can react with sodium hydroxide to give you sodium oxochlorate 1. Because of this, you don't use simple cell to produce sodium hydroxide from sodium chloride. Therefore, let us look at how you produce sodium hydroxide from in large scale using electrolysis. We are going to look at only one of them, which is, therefore we are going to look at Kerner solver cell. We're going to look at kernel solver cell. The mode of production of sodium hydroxide here is the same thing as in diaphragm cell. It's the same thing as in diaphragm cell. Let me draw this. All right. The drawing will help us explain this, even though we wasted some time. The drawing will help us to explain this. If you look at the diagram, you feed in, look at the diagram. The anode is made up of carbon or graphite. The cathode is made up of mercury. Therefore, you feed in your fresh brine. Brine is sodium chloride. Brine is concentrated sodium chloride. Therefore, you feed in your brine, which is your major raw material here, through this end. The brine comes in here. You know that sodium chloride have a melting point of 801 degrees centigrade. But if you operate this process at this high temperature, the process will not be economical. Therefore, what you do you apply your knowledge of chemistry, knowing that a solid, if you introduce an impurity, it will reduce the melting point. Therefore, what happens is that this brine is mixed with calcium chloride. The essence of the calcium chloride is to bring that to reduce the melting point. The essence is to reduce the melting point. And when you reduce the melting point will now come down to about 600 degrees centigrade. Therefore, when you now heat this thing up to the melting point, you discover that the ions from sodium chloride is NaCl. It ionizes to give you sodium ion plus chloride anion. Even though this is a concentrated solution, there is still water there. You have hydrogen ion plus hydroxide ion. You discover that this mercury cathode is a cathode that have affinity with sodium. If you look at the other process we did before, we discovered that sodium and hydrogen ion migrates to the cathode, but hydrogen is deposited. But in this case now, two of them will migrate. The one that will be deposited will be sodium. The reason why sodium will be deposited instead of hydrogen ion is because sodium have affinity with mercury. And again, the energy need for sodium to be deposited is lower than that of hydrogen to be deposited. Therefore, when you have this, you discover that your sodium will now be deposited at the cathode to give you sodium mercury amalgam. And chlorine, if you come to the, well, let's write at the anode, you have your chloride, 2 moles of chloride to give you 1 mole of chlorine gas plus 2 electrons. Then at the cathode, you now have Na plus electron, 2 electrons to give you 2 moles of sodium metal. And I've explained why sodium deposited instead of hydrogen ion. That sodium have affinity with mercury, and that the energy required for sodium to be deposited is lower than hydrogen being liberated. That is the reason why sodium instead of hydrogen, in spite of the fact that hydrogen is lower in the electrochemical series, but sodium still was deposited instead of hydrogen ion. What I've discussed now is the kernel figure. Kernel solver process. That of diaphragm is almost the same thing. They work in the same principle. Therefore, we don't need to repeat that. Then when you produce When you know that in the cathode, what we produce in the cathode is sodium mercury amalgam. One may ask, how do you now produce your sodium hydroxide? When you have produced your sodium mercury amalgam, the next thing is that you dissolve it in water. When you dissolve it in water, you will have sodium hydroxide plus mercury. Then the next thing is hydrogen gas. The hydrogen gas is liberated, while you now have I think the equation is balanced. Sodium is 2. Oxygen is, all right, there should be 2 here. Sodium is 2. Oxygen is 2. And 2 is here. Hydrogen is 4. Hydrogen is, you put 2 here. That's 4. Which means we can equally do it this way without putting we have sodium hydroxide plus mercury plus hydrogen gas. Let's look at whether sodium is 1, oxygen is 1, oxygen is 1, hydrogen is 2, hydrogen is 2. Therefore, you don't need to put the 2. That's how you produce your sodium hydroxide. The sodium mercury amalgam is dissolved in water to give you sodium hydroxide, mercury, and hydrogen gas. The hydrogen gas is liberated out of the system. The mercury, you will now recycle it because you are using mercury as your cathode. Therefore, you will now recycle it back so that it will be serving as your cathode. Let's look at physical properties of sodium hydroxide. Physical properties of sodium hydroxide. All right, these ones you can just write so that we don't waste our time. Physical properties of sodium hydroxide. Sodium hydroxide is a solid at room temperature. Or call it sodium hydroxide is a white crystallized solid at room temperature. 2. Sodium hydroxide, when dissolved in water, is alkaline. That is, it turns red litmus paper blue. Then sodium hydroxide is also deliquescent. All these things, you know them already. Deliquescent is when a solid, when exposed in air, dissolved to form a solution. Therefore, sodium hydroxide is deliquescent. Let's now look at, all right, let me recast your physical properties. I said that sodium hydroxide is white crystalline solid at room temperature. I said that sodium hydroxide is deliquescent, and you already know what deliquescent is. And thirdly, I said that when you dissolve sodium hydroxide in water, the solution is alkaline. That is, it turns red litmus paper blue. Let's look at chemical properties. Chemical properties of sodium hydroxide. You already know that sodium hydroxide is an alkaline, and those properties of alkaline is almost the same thing, but It's not that it's the same thing, not almost the same thing. It's the same thing, but for purposes of emphasis, let me repeat them again. But you already know them. Chemical properties. One, sodium hydroxide, when exposed, sodium hydroxide, when exposed to air, reacts with CO2 from air. When it reacts with CO2 from air and the moisture from air, it will give you, you have this equation. Sodium, all right, let's call this exposure to air so that we don't copy so much. You have sodium hydroxide reacting with CO2 in the atmosphere plus water vapor in the atmosphere to give you sodium trioxocarbonate 4 plus water plus water. You now check whether the equation is balanced. Hydrogen here, so you have 2. Sodium is 2, sodium is 2. Hydrogen here is 4, hydrogen is 4. Carbon is 1, therefore is balanced. When sodium hydroxide is exposed to air, it forms sodium trioxocarbonate and water. For let's look at 2. Neutralization reaction, you know what it means. You know that when sodium hydroxide reacts with an acid, it will form salt and water only. Then the third one, sodium hydroxide reacts with acidic gases to form corresponding acidic salt. For instance, sodium hydroxide reacting with SO2, it will give you NaHSO3. This is an acidic salt, or an acid salt. Then the fourth one, as precipitating agent. As precipitating agent. Sodium hydroxide reacts with metallic salt to precipitate trioxocarbonate 4 and hydroxides. For when you react sodium hydroxide with metallic salt, when you react sodium hydroxide, Eb and O3, We have PB hydroxide plus 2NaNO3. This lead hydroxide is a precipitate. So sodium reacts with metallic salt to precipitate trioxocarbonate 4, alright, or hydroxide. In this case, it precipitated hydroxide. Let's look at sodium hydroxide, the fifth one. 5. Sodium hydroxide reacts with chlorine gas to give or to produce oxochlorate 1 and oxochlorate 3, depending on the condition. Let me repeat this. I said that sodium hydroxide will react with chlorine gas to produce oxochlorate 1 salt or oxochlorate 3, depending on the condition. Let's look at the conditions. If you are using cold sodium hydroxide, you produce oxochlorate 1. If you are using cold sodium hydroxide, you produce oxochlorate 1. Cold and dilute sodium hydroxide. Cold and dilute sodium hydroxide. Cold and dilute sodium hydroxide, I'll just say it and then put the equation on the board. Cold and dilute sodium hydroxide reacts with chlorine gas to give you sodium oxochlorate 1 and sodium chloride. Therefore, you have NaOH reacting with chlorine gas to give you this is your sodium oxochlorate 1. You know sodium chloride. This is when it is cold. For the other condition is hot and concentrated sodium hydroxide. And I say that if sodium hydroxide, hot concentrated sodium hydroxide react with chlorine gas, it will give you sodium trioxochlorate 5, sodium hydroxide and water. Therefore, the equation is this. You have, since we say concentrated sodium hydroxide, it will be 6 moles of sodium hydroxide reacting with 3 moles of chlorine gas to give you sodium trioxochlorate 5 aqueous plus 5 moles of sodium chloride plus water. Right, let's look at how we will balance the equation. Since there is 6 moles here, therefore hydrogen will be 6. Therefore you put 3 here. We'll look at chlorine. Here is 6. Chlorine here is 5 plus 1, 6. This compound is called sodium trioxochlorate 5. Therefore, you can go to an examination and they'll ask you, in code, sodium hydroxide, if you react with chlorine, is going to give you the major product will be sodium oxochlorate 1. If it is concentrated and hot, it will give you sodium trioxochlorate 5. Let's now look at uses of sodium hydroxide. Uses of sodium hydroxide. All right, this one is important. I wanted to leave some of them. This one is important. Reaction with glass. Reaction with glass. Sodium Sodium hydroxide can react with glass to form sodium trioxosilicate 4. That is the reason why you don't use glass stoppers to cork your sodium hydroxide. If you have a glass bottle and you fill it with sodium hydroxide, you cannot use a glass stopper to close it. If you close it with glass stopper, if it goes on for a period of time, maybe up to 1 month, if you want to open it, you cannot open it again. It is because of the reaction between the sodium hydroxide and the glass. Therefore, you can write sodium hydroxide attack glasses, especially when heated. Why it attacks glass is because glass contains silica, and silica is SiO2. Simply put, silica is the major component of sand. Silica is the major component of sand. Therefore, when you react sodium hydroxide reacting with to give you sodium two here, two here, two here. All right. This is the reaction. It will form this one. This compound is called sodium trioxosilicate. This is -6. This is +2. Silicate 4. Therefore, you don't use glass stoppers or rubber stoppers to cork your sodium hydroxide. But the next one is uses of sodium hydroxide. Uses of sodium hydroxide. I know by now you should have known some of the uses of sodium hydroxide. You have done acid-base titration. Therefore, at least what should come into your mind is that sodium hydroxide is used in acid-base titration. Sodium hydroxide is used in acid-base titration. It's in the lab. It's a lab reagent. 2, you have come across the fact that you use sodium hydroxide in producing soap, in production of soap. 3, when we did chemical industry, some of these uses are there. You can equally use sodium hydroxide in water treatment. It's used to remove both temporary and permanent hardness. You can equally use sodium hydroxide in production of rayon. You can equally use it in crude refining. To remove the slimy, slippery distance in crude. 6, you can equally use in absorbing CO2. There may be a reaction. For instance, when you want to purify air, you pass air through a filter, it will remove the dust. You pass it through sodium hydroxide to remove the CO2 before you now do distillation to separate other components. 7, where we will stop, you can go and use in bleaching of textiles. These are the uses of sodium hydroxide. I think we can stop here. When we come next, we'll look at sodium triosocarbonate and sodium hydrogen triosocarbonate. Let me rehearse what we have done already. What we did today is to look at compounds of sodium, and then we selected sodium hydroxide. We look at how sodium hydroxide can be produced. The one that can be done in the lab and the one that can be done industrially. The 2 methods of production of sodium hydroxide is from Gossage process and electrolysis. We say that the Gossage process is the reaction of sodium triosocarbonate and double decomposition of sodium triosocarbonate plus look at sodium triosocarbonate and calcium hydroxide to give you sodium hydroxide. Then we look at the electrolytic process. In the electrolytic process, we said that we can produce sodium hydroxide by using Kenner solvent process and diaphragm cell. In the Kenner solvent process, we discovered that the anode is made up of carbon and the cathode is made up of steel. The anode is made up of carbon and the cathode is made up of steel. We saw that in the anode, the chlorine gas is liberated there. In the cathode, the hydrogen gas is liberated there, leaving behind sodium ion and hydroxide ion, which is your sodium hydroxide. Then we looked at we talked about Gossage, we talked about using Kenner solvent process. And I said we have another method, which is diaphragm. And I said that it is working in the same principle as the first one. The only thing is the cell being differently. Then we looked at physical properties of sodium hydroxide. We say that sodium hydroxide is deliquescent. We say that when you dissolve sodium hydroxide in water, that it gives you an alkaline solution which turns red litmus blue. We say that sodium hydroxide is deliquescent. That is to say that it absorbs moisture from the atmosphere to form a solution. Then we looked at the chemical properties. We saw that when you expose sodium hydroxide in air, it will form sodium trioxocarbonate 4. Then we looked at the reaction of sodium hydroxide with an acid. We say that it's neutralization reaction. When sodium hydroxide reacts with an acid, it will give you salt and water only. We looked at sodium hydroxide, its reaction with chlorine. We say that the reaction of sodium hydroxide with chlorine depends on the condition. If it is sodium hydroxide dilute and cold, that what you have will be, as major product, will be sodium oxochlorate 1 and sodium chloride. And we say that if it is hot and concentrated sodium hydroxide, what you will produce will be sodium trioxochlorate 5 and sodium chloride. I think with this, we have gotten some of the important things we need to know here. The important thing is that you should be able to write the chemistry of the reaction, which is for you to know what happened at the cathode and what happened at the anode. I said that what happened in the anode is oxidation and what happened in the cathode is reduction. And the ability for you to write down the equation. For your evaluation, question, you can write number one, name the two types of cell used in manufacture of sodium hydroxide and give the electrode used in the two cells. And give the electrode used in the two cells. Then the next one is list 5 uses of sodium hydroxide in industry. Then 3, explain the reason why in the Kerner-Solvay process at the cathode, sodium was deposited instead of hydrogen ion, in spite of the fact that hydrogen is lower, very much lower in the electrochemical series. I said, explain the reason why sodium ion was deposited at the cathode in the Kerner-Solvay process, in spite of the fact that hydrogen ion ought to be deposited. Thank you for listening. I still remain your chemistry teacher, Mr. Odemenam Chidube. I hope you are reading your books, because whenever this situation ends, or whenever it comes to a manageable level, if you come back to school, I assure you, you may not stay more than 2 weeks and the WAEC will be taken. Goodbye and be blessed. Thank you.